In section 2.4, we're looking at algebraic limits. So this is going to be better than, like, for example, section 2.3, where you could just plug the limiting value into the expression and f of a was the limit as x approaches a. Okay, so what happens if a is an undefined value on the original function? Well, fortunately, anytime that the limit does exist as x approaches a, there's also going to be a beautiful algebraic solution that enables us to find that limit. Let's go ahead and take a look at this together. So whenever, let's see here, let me maximize that. There we go. Whenever we look at algebraic limits here, the first one I'm going to start with is one that we could not evaluate by hand, or at least by just plugging in the 5. If I say evaluate the limit as x approaches 5 of 25 minus x squared over x minus 5, I can't plug the 5 in, because if I try, it's going to lead to a 0 over 0. Anytime you have that 0 over 0, we know that the function is undefined at 0. Well, the limit is of indeterminate form. So we don't know if there's a limit as x approaches 5. That's what indeterminate means. It means there could be an answer, could also be undefined. We don't know right now. It's indeterminate. So we try to put this function into a better format that might enable us to evaluate the limit. Like I was saying, anytime the limit does exist, an algebraic solution will exist. So the factor that's causing this function to not exist is going to cancel out. So please notice, if I say, okay, let's factor that numerator, difference of two squares, it's going to be 5 minus x, 5 plus x. Now I knew I had a factor of x minus 5 in the denominator, and I knew that that x minus 5 has to go away. Because as long as it's there, I can't plug a 5 into that function because I have a 0 in the denominator. All right. So since the numerator factored to be 5 minus x and 5 plus x, I'm going to go ahead and factor a negative 1 out of the denominator. And when I do, that's going to become a positive 5 and a negative x. So I get 5 minus x. Now, I see I have a common factor of 5 minus x in the numerator and denominator. So this limit as x approaches 5 is going to simplify down to 5 plus x divided by negative 1. Can I now apply the limit as x approaches 5? Sure. Because my denominator is negative 1, this function is going to be defined at 5 now. I can plug a 5 in, and I'll get 10 over negative 1. This function has a limiting value of negative 10. Now, whenever we're looking at this problem and getting that limiting value of negative 10, the question arises, yeah, but is what you've done legal? Because people would say, but 25 minus x squared over x minus 5, maybe they think it doesn't equal the negative of the group 5 plus x. Notice that's the same thing as what I have. It doesn't matter whether you multiply by negative 1 or divide by negative 1. I'm essentially saying this is equal to this. And you might think, well, can you say that that's equal to that? And you say, well, yeah, you absolutely can, because this simplifies to this expression. So yeah, they're the same thing, with the exception that the original function has a domain restriction at 5. This function doesn't. Do I care that the original function could not exist at 5? And you should be thinking, no, you could care less what happens at 5. We're trying to show what happens as you get infinitesimally close to 5. So the fact that the original function does not exist at 5 has nothing to do with what the limit approaches as x approaches 5. And anytime that limit exists, an algebraic solution is going to exist to enable you to cancel out that factor that's causing the denominator to be 0 in this case. So we can say, well, yeah, my algebraic simplification of that original is the same as the original for all values except 5. And when I'm trying to find the limit as x approaches 5, I don't care what happens at 5. I only care what happens as we near 5. So this process is going to work beautifully every time. Now, let's take a look at another problem here. If I say, I want you to find the limit as x approaches negative 6 of the quadratic x squared plus 3x minus 18 over x squared plus 11x plus 30. So as soon as I see this, and I'm saying, well, it's the limit as x approaches -6. I could try plugging in a -6 in the denominator. It would give me 36 minus 66 plus 30, which would be 0. So I know, it's going to be undefined. So I can't just plug in a -6. I'm going to have to try to algebraically simplify it. The fact that I know that -6 gives me a 0 in the denominator means automatically x plus 6 had to be a factor of that denominator. That's the only factor that's going to be 0 as x approaches -6. So you can use these limits to help factor your problems. Could have I sat there and said, well, I need to find factors of 30 that sum to get to 11 and say, well, 6 times 5 is 30, 6 plus 5, I could have. But this makes it even easier. I knew from the very beginning x plus 6 had to be a factor in that denominator. And now, since -6 gives me a 0 in the numerator as well, x plus 6 had to be a factor in that numerator. The numerator is going to be factors of -18 that sum to get to 3, +6 and -3. Now that after you've factored out your expression, you can cancel out the factor causing trouble. The x plus 6's are common in the numerator and denominator, so they cancel, which leaves me the limit as x approaches -6 of x minus 3 over x plus 5. Now I can plug the -6 in, so notice from this step to this step, I drop the limit notation. That's a common question students have. When do you put the limits and when do you not? Well, the time you drop the limit notation, every step requires the limit notation until you can physically, in this case, plug a -6 in for x. When I plug a -6 in for x, I'm taking the limit, so the limit notation must disappear. And I can say, well, my numerator is going to be -9, my denominator is -1. This final limiting answer is 9. Now, sometimes the old problems, like in section 2.3, will pop back up. So if you can plug the value into the function, you should. Now, this one's a bit tricky because you'd almost think, well, no, wait a minute, John, you can't plug that in. Yeah, you can. Because if I plug a -4 in for x, my denominator is not 0, it'd be a -8. So when you can plug the value in, you should. And in this case, I'd get -4 squared plus 16 divided by -4 minus 4. This gives me 32 over -8, which has a limiting value of -4. So as x approaches -4, the y value will approach -4. Now, I could have asked the more interesting question here, what would be the limit of this function as x approaches 4? And you'd say, ooh, well, wait a minute. You can't plug a 4 into that denominator. 4 minus 4 is 0. So if you can't plug it in, you'd say, well, the only way I could evaluate the limit is if there's some algebraic simplification. But look at that numerator. Sum of squares is non-factorable. So you'd say, well, x squared plus 16 doesn't have a factor of x minus 4, so there's no way I could ever cancel out that factor in the denominator that's causing this to be undefined. So in this case, you'd say, since there's no algebraic simplification, there is no limit that exists as x approaches 4. And I guarantee you, if you graphed this function out, you're going to have a vertical asymptote at 4, and you'll see that as x approaches that, one side's going to go to infinity, the other side's is going to go to -infinity. There's not going to be a limit as x approaches 4. Now, if I look at what about the problem limit as h approaches 4 of 9h minus the group h plus 2 squared over h minus 4. As soon as I start this problem, I can say, well, I know I can't just plug a 4 in because it gives me a 0 in the denominator. So every single step I'm doing in the remainder of this simplification, it's with the end goal of, I have to get a factor of h minus 4 in that numerator. If I cannot, then this problem does not have a limit similar to the previous one here in the second part of it. So I can say everything I'm doing is to try to get a factor of h minus 4 in the numerator. So the first thing I do is I go ahead and square out h plus 2 as h squared plus 4h minus 4. Now we're subtracting that whole group, so my numerator becomes -h squared plus 5h minus 4 all over h minus 4. And this is still inside of the limit. So since I don't like factoring a trinomial with a leading term that's negative, I'm going to go ahead and factor that negative 1 out of the numerator and get h squared minus 5h plus 4. Now I can say I am 100% confident that this trinomial that remains, it better have a factor of h minus 4, or this limit does not have an answer. And I can say, well, sure it does. Factors of 4 that sum to get to negative 5, negative 4, negative 1. That h minus 4 cancels out in your numerator and denominator, and you can say your final limit notation is going to be the limit as h approaches 4 of negative 1 times h minus 1. Then you can say, all right, can I allow h to go to 4 now? Sure you can. Plug a 4 in for h, you'll get negative 1 times 3. Negative 1 times 3, final answer of negative 3. Gorgeousness. Now, if you're thinking, well, I want to see even more fun problems. On the next page, I talk about the things that you'll typically need to consider. And one of those I mentioned here is with the square root expressions. Let me show you what I'm talking about with the square root expressions. If I ask you to evaluate something like the limit as x approaches 9 of the root of x minus 3 over x minus 9. Okay, so you know you can't just simply plug the 9 in. It would give you a 0 in the denominator. It also gives you 0 in the numerator. So I can say, well, there's got to be some algebraic simplification. Here's what I do. I can say that original problem is equal to, and what am I doing in my numerator and denominator here? Anytime you see a square root as part of a binomial, you know you can write an expression without that square root if you multiply by the root conjugate, which is the same two terms with the opposite sign in between. So now, whenever you multiply by that, you can't just multiply the numerator. You'd have to multiply the numerator and denominator by the same term. Now, please don't distribute out in the denominator. The whole point is to leave that denominator factored. I know I've got to get rid of the factor x minus 9 or this problem can't be solved. So I leave the denominator factored. I go ahead and FOIL the numerator. And the whole point for multiplying by that conjugate is now I'm going to get an x minus 9 up there. You'd have the root of x times the root of x. The middle terms always cancel when you multiply by the conjugate. Last term times last term gives you the minus 9. Now that I see I have that x minus 9 as a factor in my numerator and denominator, everything is going to be fine because those x minus 9s cancel. And that's going to leave me, when everything cancels in your numerator, you have an understood 1. Your denominator, the root of x plus 3. We can now evaluate the limit as x approaches 9 of this expression, and we get 1 over the root of 9 plus 3. That gives us 1 over 6. Gorgeousness. Now, if you're thinking, well, hey, that was a pretty cool problem, but is there an even cooler way to work it? Oh, yeah. I would prefer you do this. So most of the time, teachers have you recognize, ooh, if you have a square root as part of a binomial, you multiply by its conjugate, and you have to do that in the numerator and denominator. That's true. All right, but an even better way is to factor the denominator of this expression. I want you to factor using the difference of squares formula. A squared minus b squared is equal to a plus b times a minus b. Now you might look at this and say, but the first term's not a perfect square. Sure it is. X is equal to the root of x times the root of x. So x minus 9 is equal to the root of x plus 3 times the root of x minus 3. And then you say, well, now that root of x minus 3 cancels, and you're left with the exact same 1 over the root of x plus 3 left inside of your limit, which leads you to that same answer. That's the more efficient and I would say better way to think of that problem. Now, this forcing the difference of two squares doesn't always help. Here's an example of a problem where it wouldn't help. My goal is not to rewrite the numerator as the root of x plus the root of 10 and the root of x minus the root of 10. Why? Because I don't see that in the denominator. It wouldn't help to do that. Now, can I just evaluate the 10 into the function? And I can see, well, no, because it'd give me a 0 in the numerator. You give me the square root of 4 minus 2, which is 0 in the denominator. So my goal is to simplify out, and I really don't have an option here. I'm going to have to try to simplify that denominator by multiplying by its root conjugate. I do that. And now when I multiply by the root conjugate in the denominator, I'll get the group x minus 6 minus 4. My numerator, I leave factored. I know I'm hoping to cancel out that x minus 10. I can do that now in the next step because I see that my denominator simplifies to give me x minus 10. The x minus 10s cancel, and I'm left with the limit as x approaches 10 of the remaining term. There is no denominator other than an understood 1 left. And you could say, so you have the limit as x approaches 10 of the root of x minus 6 plus 2. You got the root of 4 plus 2. That's going to give you a final answer of 4. Pretty good stuff. Now, I also mentioned that sometimes you'll need to use difference of cubes formula. Please do remember your difference of cubes formula is a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. If it were sum of cubes, the only difference is you have a plus sign here and a minus sign here. That's it. They're the same formula other than that. Now, anytime you have a complex fraction where you have fractions inside of a fraction, your goal is to get rid of every single denominator of the terms on the inside. So you should be thinking, well, how do I simplify this? You need to multiply by the least common denominator of all denominators in there. The least common denominator constant is a 125 because I know it's going to get rid of that term and that term. As far as the variable, if I multiply by an a cubed, it'll get rid of both of the denominators of a. So I can say I'm going to multiply by 125a cubed in the numerator and denominator. When I multiply that in the numerator, my first term is going to be 125a squared. My second term, 1/5 times 125, that's going to leave me minus 25, and I'll still have the a cubed. When you distribute that in the denominator, the first term is just going to be a cubed. And the second term, the a cubed cancels, and you'll have minus 125. Now, I need to recognize that denominator is a cubed minus 5 cubed. So in the next step, I can factor it as a minus 5 times a squared plus 5a plus 25, following your difference of cubes formula. Your numerator, all I'm doing is I'm factoring using greatest common factor. I factored out a 25a squared. But now at this step, I'm still not quite to the point where I can cancel anything out. I know this is the factor I want to cancel out because it's causing a 0 in the denominator. I can easily cancel that out if I could rearrange the terms in this. I can do that by factoring a negative out. That's why this negative comes out in front of the 25a squared. And then this group's going to become positive a minus 5. Those groups at a minus 5 cancel. And I have my negative 25a squared over my trinomial in the denominator with respect to a. At this point, you can go ahead and let a go to 5. Your numerator becomes negative 25 times 25. Every single term in the denominator becomes 25. So you have 25 plus 25 plus 25. That's 3 times 25. Your numerator is negative 25 times 25. So the most efficient path to an answer would just be a. Cancel out the factors of 25 and you've got negative 25 over 3. Alternatively, you could have said, well, negative 25 times 25 is going to be 625. Your denominator is 75. That still reduces down to negative 25 over 3. What if you have exponential functions inside of a limit? All I need you to remember with exponential functions is please remember anytime you multiply the common base, you add their exponents. So 10 to the 2x is nothing more than 10 to the x times 10 to the x. So if you have a problem and you're asked to simplify it like this, and you say, well, I can't just plug the 0 in because that denominator is going to be 1 minus 1. It's a 0. How do I simplify this out? Well, you simplify it out by taking a greatest common factor in your numerator by understanding 10 to the 2x is 10 to the x times 10 to the x. So you can factor a 10 to the x out of the numerator and you'll get 1 minus 10 to the x. That cancels with your 1 minus 10 to the x in the denominator. And then you can say, all right, this is going to be the limit as x approaches 0 of 10 to the x. Let x go to 0. You've got 10 to the 0, which we know is 1. Pretty cool stuff. And how could we not at least do one example with trig? With these examples with trig, I need you to think about what we did up here. And you might not see it to begin with in this problem. You say, well, I don't have any fractions in there. Yeah, you really do. What I needed to understand is this secant is 1 over cosine. And then I have minus cosine over sine. So I'm thinking of this as a complex fraction. The secant is creating a fraction within this fraction. So I'm thinking, well, it would be better if I didn't have that 1 over cosine in there. So let's take this expression, get rid of that secant by multiplying by cosine in the numerator. And if we do that, we also have to multiply by cosine in the denominator. Now, I know the end goal is to get rid of that sine of theta in the denominator, because if theta is going to go to 0, the sine of 0 is 0. That cannot stay down there and me be able to get a real answer out of this. So I'll say, okay, my goal is to factor out a sine theta. The first step in that goal is to simplify my problem by multiplying by an understood 1 of cosine theta over cosine theta. When I do that, 1 over cosine times cosine gives me a 1. Cosine times cosine, cosine squared. My denominator, I just leave as factors, sine theta, cosine theta. But now you should be thinking, fantastic, that's one of your fundamental trigonometric identities, or I should say fundamental Pythagorean trigonometric identities. 1 minus cosine squared is sine squared. So now that I have that sine squared theta in the numerator, that can and should be canceled with that sine theta in the denominator. And I can say, well, this just simplifies to sine to the first over cosine. Now, if I let theta go to 0, the sine of 0 is 0, cosine of 0 is 1. Your final answer is 0. Now, that will do it for the examples for this section. Please do try the Achieve homework for section 2.5. There's some fun problems in there. Also, if you run into any trouble, check against the video that I've done where I show you how I do all of the problems in that section. And after that, let me know if you have any questions. I'll be happy to help.